So hello, today we are going to finish chapter 22. I know what chapter we're on, really. Um, chapter 22 of Physics 155. We've been talking about current and resistance, and now we're going to get into the really hard part. Yeah, this video is probably my most complicated one mathematically. Um, so if you're watching it, good on you. If no one ends up watching this, you're basically screwed. So that'll be fun. Yeah, we'll see how it goes. So we were talking about resistors in parallel and series. And if we have a group of resistors in parallel and series, we can solve for equivalent resistance. When we solve for equivalent resistance, we can then go and try to find the current and voltage on each one. Well, that's only if we have a more simple setup where we can easily break it down. Sometimes you have multiple batteries in, or maybe we may throw something else like a capacitor in. What we're going to talk about today is how to deal with a complicated circuit that either can't easily be broken down to parallel and series due to extra batteries or what have you, or, as I said, if it also has a capacitor. And we'll kind of do them one at a time. Let's start with just the what if there, well, in general, for either one. If it has a capacitor or if it's just more complicated, either way, we are going to use something. Hey, someone actually logged in. We are going to use something called Kirchoff's laws. So, or Kirchoff's rules. Kirchoff's rules say the following. What they are, it's just a set of rules, two rules only, to let you find the current through every resistor in a circuit. And what it is these rules will let you make a series of equations that you'll solve to find the current through each resistor. Now, how to do it? Not so complicated. The math you need to use to solve Kirchhoff law problems is the most complicated math we will do in this class, hands down. It is messy, it is ugly, it is a pain in the ass. I'm sorry, it just is what it is. Here's the general idea. The two rules are as follows. The first is the junction rule. And the junction rule says that at any junction, the current going in it must equal the current going out. This is from the law of conservation of charge. But basically, if we have 20 amps going into a junction, 20 amps better leave it. If it doesn't, that means, because current is moving electrons, that would mean electrons are just disappearing or appearing, depending if it's less or bigger or smaller. And we're just going to say that for any junction, current in equals current out. The second law, or rule I should say, second rule, it's not really a law, is that the sum of potential differences across all elements in any closed loop must be zero. That in any closed loop of a circuit, the total potential, adding up each piece in the loop, must be zero. Now, this is the messy part. This is the part that is the easiest to make a mistake in. And as I do these problems, I'm sure you're going to see me mess them up from time. Actually, no, the math is the easiest part to make a mistake in these. The math is not going to be fun, as I said before. But this is an easy part to mess up. So be careful. But here's the general idea. Resistors use potential. Resistors take potential and reduce by a potential. So when you're going around a loop, what you're going to do is you are going to work around a loop. And you'll see what I mean when I do an example in like one slide, two slides. When you work around the loop, you are going to say, I'm going from here to here to here to here to here. If you are working around the loop in the same direction as the current, you must say every time you pass a resistor that they lose a voltage equal to IR. aka when you go above a resistor in the same direction of the current, you're going to say minus IR at that point to the potential. Now, if you're going around the loop the other way, like, let me get my pen. If I actually had a full loop here, which I don't, if I was taking this loop and going from here to here to here, I would be making my loop going the opposite way of the current. If you're making your loop in the opposite direction of the current, then you can add IR instead. This is a very easy thing to mess up. But if you're going in the same direction as the current, you subtract IR. And we now have people in, so hopefully ask questions as you need it. Oh, why are you not doing what I want you to do? Fine, be that way. Now, resistors use up the potential, but batteries can give you some. And we talked about last class a little bit about EMF in a battery. Neopositive, no, I didn't talk about EMF yet I already used this symbol. That is a mistake that I should fix. Yeah, I don't talk about it later on. I need to change the order here. This is a mistake. But we actually will sometimes use this E to represent voltage. Actually, you know what? I'll just explain it real fast and then come back. I'm sorry. I got to fix that in my notes. We often with a battery will say that the voltage they supply is the EMF, central electromotive force. EMF is just a fancy way to say voltage, but it's voltage supplied by a battery. It's just a way to say, hey, this battery, it applies this much voltage. So you'll sometimes see that curse of E there instead. As I said, I'll come back and do that in more detail. For now, it's not too important. When you pass over a battery in the same direction a battery likes to go, which is from negative to positive, if you travel across a battery when you do your loop from negative to positive, you add that much voltage. If you go in the opposite direction, if you go from positive to negative, you're going against the battery and you subtract that much voltage. Now, this is assuming a full loop. You can actually just say, if you don't have a whole loop, what's the potential difference between points, and use these same laws. That if I say the potential difference between A and B, for the first one, it's negative IL. For the next one, it's positive IL. For the one after, it's the voltage of the battery. The one after, it's negative voltage of the battery, which is what's written on this slide. But these are the Kirchoff loop rules. What it's going to say is that in any loop, well, in any junction, current in equals current out. And on any loop, the total potential is 0. Well, it's going to be, well, what you do with the potential when you pass each thing will depend on which direction you're going and if it's a battery or a resistor. I said we're going to use this for capacitors also. I'm only going to slightly touch on what this means for capacitors, but it will be the same general idea. Capacitors will also lose potential going the correct way. It's just we don't have as easy of an equation for capacitors. So this is what I mean in practice. This is one of those things that I think explaining it doesn't help at all. Like it just doesn't, it's hard to follow. But when I do the actual doing it, this will make a lot more sense. So this is how you do a Kirchoff law problem. Now this problem is pretty simple. I could do this with equivalent resistance and stuff. But let's say I wanted to know the current through each resistor here. That's normally how a Kirchoff law problem starts. Where I have a resistor R1, R2, and R3. And I have a battery that I called VB for battery. If I want to know the current through each resistor, what you're going to do, how you do this, is you take a look at each resistor and you decide what your currents are. You label your currents. I call them I1, I2, I3 because that's the current on resistor 1, 2, and 3 respectively. Of note, every time you have a junction, current can change. And so every time you hit a junction, your I needs to change. And that's why I have one I, let me get my pen again. One current for all of this, then one current for this, and then one current for this, is because that's in between each junction. That this, from there to there, I am just making a mess. Erase pen. That from here to here is I1. From here to here is I3. From there to there is I2. that each region in between junctions is a current. Now this means we're going to solve for three currents: current I1, current I2, current I3. We have three unknowns. There's a rule in algebra, I don't remember the name of it, that if you have multiple unknowns, you need as many equations as you have unknowns. So if I have three unknowns, I need three equations to solve this, which is why the math is going to get ugly. Once you define each current, you guess the direction of each one, and you just say what direction each current is going in. It doesn't matter if you're right. Just pick a direction, any direction. Make sure you keep track of what direction you picked, but just guess. And I'm going to say, you know what? I1's going that way. I2's down. I3's down. Why did I pick those directions? Made sense to me. The battery is driving it, so the battery's going to push up. They'll probably both go down. Doesn't matter if I'm right or wrong. Just guess and mark down what your guess is. This is going to be important. See, we will know exactly which direction they're going in. And when you solve for currents, if you ever get a negative answer for your current, that means your guess was wrong. And it means the current's just in the opposite direction from what you guessed. Once you have that set up, you can begin to solve. And this is what you do. I always recommend, if you have three unknowns, to do one junction rule and two loop rules. If you have more unknowns than that, you need more equations. So you're going to have to figure it out. But let's say I look at this. I like to start with my junction rule. See, what I'll do is I'll pick a junction. And it doesn't matter which junction. I'll pick any of the junctions. I used this one. And I'll follow the junction rule. And I can look at this and say, okay, current I1 enters that junction. Current 2 and 3 leave that junction. So therefore, with the junction rule, I can say that I1 equals I2 plus I3. The current in to here, and I'll keep drawing, the current into here equals the current out of there. Does that make sense?
Yep.
So now let's do the loop rule. Loop rule is a closed loop. And when I say a closed loop, you're going to pick a loop, and I don't want that to go yet. So I'm going to start at any spot, and I chose the bottom left corner because I felt like it, and I will look at any closed loop. There's actually three options here for closed loops, not including just doing the same loop in the opposite direction. See, I can say my loop is starting at that corner and going up there and down there. That's a closed loop. I could say I can go up and do the whole thing. I could also say my loop is this little guy, which that really lagged on my computer, so I'm going to do it again in case it did it for the video. All of those are loops. They are a closed loop. And on any three of those loops, be it the left one, the right one, or the whole thing, the total potential must be 0. Now, I have three unknowns, so I need three equations. And I only got one equation. I got my junction rule equation, which means I need two loops. So I'm going to pick what two loops to use. And here's the thing. It doesn't matter which ones you pick. It'll always work out. You pick two, you can make the math work. I'm going to arbitrarily pick the two that I arbitrarily picked, but you can pick any two you want. So I'm going to do this guy first for my first loop. So that's the loop. I want to go and figure out the potential over that loop. And what I would say is over any loop, the sum of the potentials must be 0. And I will work my way through it. See, what this does, if I follow this loop, is first, I go up past the battery. I pass the battery in the same direction as the battery. That means I add a potential V. I then go across here. I pass the resistor in the same direction of the current. Now note, the battery doesn't care what direction your current is. The battery cares if I'm going from negative to positive. The battery I pass going from negative to positive, we're good. The resistor I pass with the current. When you pass the resistor with the current, you then subtract. And so I have to subtract the voltage drop over the resistor. But we know Ohm's law, voltage drop on a resistor, V equals IO. So the voltage drop over this resistor is I1 all 1. And once again, it's negative because I'm with the direction of my current, following those same rules I had before. I'm then going to continue my loop, and I'm going to finish it. I'm going to go, that didn't do anything. I'm going to go down and over, and I finished my loop. But as I finish my loop, I pass over resistor 2. And so I have the potential drop on resistor 2, which is also negative because I'm going with the current, and will be I2O2. And there we go. That's my loop. I know the voltage of the battery minus I1O1 minus I2O2 must be 0. Okay, I need another loop. So I'm going to pick this guy. And I'm going to say, okay, on that loop, the total potential must be 0. So let's work our way through. Well, I start by going up like this. I went up, but my current pointed down. I went in the opposite direction of my current. Therefore, I don't subtract I2O2, I add it, because I opposed my current. I went in the wrong direction. I then pass over I03, but I passed O3 in the same direction as the current. So that gets subtracted, negative I3O3. And that was my closed loop, right? I went up and then over. So there's my loop. So there's my third equation. Now, any questions on how I got those equations? Will I get a chicken waddle? Okay, that is the kind of annoying part, but honestly, that's not the complicated part here. See, now it's like, okay, I have 3 equations, and your goal is to solve for each current. What I'm going to have to do is solve for all of my things. And at this point, it's algebra. I can't just say, oh, follow these steps. How you do it, it changes each time. Normally, what I do is of my 3 unknowns, whatever is in both of my loop equation, and I said, this is what I normally do. I won't say this is what I always do. But whatever unknown is in both, as in I have I2 here and I have I2 here, I'll solve for the other piece. AKA I'll solve for I1 and I'll solve for I3. I'll solve this equation for I1 and plug into here. I'll solve this equation for I3 and plug into there. Because if I do that, I'll have I1 with respect to I2. I'll have I3 with respect to I2. And this top equation will only have I2. I don't know how much sense that made saying it out loud, but I'm going to be doing it right now. So I'm going to start with this equation. And actually, I just said that's the way I normally do it, and I did it differently this time. I did it differently. Okay. And I'm going to say, okay, I can add I3O3 to both sides. If I add I3O3, and I said I always did it one way, and I'm doing something different, I should pay attention to my own notes. I'll just divide both sides by O2. I got an equation for I2 now. And that's really, no matter what you're going to do, you have to solve for various pieces. And I can say I2, you know what? I'll shove that into that equation up there. That I1 equals I2 plus I3. I just factored my I2 into my loop equation. Ooh, I see what I did here. I did this kind of weird. And I'm like, here's an equation for I1. But that I1 yeah, is this I1. So I'm just going to shove that in there. And say that VB minus I1 times R1 minus I. Hold on. Oh, yeah. And I also did, I see what I did. I2O2, but I2O2, as I have up here, is I3O3. So I shoved that in too. Sorry, I will try to explain this better. As I said, these are already done. So I took this I2O2 and used this guy. And I took this I1 and use that guy. You follow? As I said, the math is really ugly on these. What this gets me is an equation where the only I is I3. So I will go and say, factor out an I3 from inside my parentheses. If I factor out that I3, I can then say, I took all the negative stuff and added to the other side. So I had 2 negative terms. I just added them to both sides. From this side, I will factor out my I3s. That's a lie. What did I do? Oh, I factored in my all 1. Then I can factor out my I3s and divide with plugging in my numbers and get a value. Now I said it and I'll say it again. The math on these is ugly. It just is. You're going to get 3 equations, 3 unknowns. You got to solve them. If you know matrix algebra, you might know a shortcut. I honestly don't really remember how to do it doing the matrix algebra shortcut because I haven't done it since undergrad. It's been a really long time since then. Like, really long time since then. But once you get your 3 equations, you go and you plug them together till you can get one of the currents. Once you get one current, you can use it to get the other ones. I2 is I3 R3 over R2. I can plug in and get the value. I1 is I2 plus I3. I can get a value. And so, yeah, you just start. Once you have your equations, you'll rearrange however you need to. Okay? So, when I did this, all of my answers were positive. That means all of my guesses for the direction of I was correct. And so I know the direction of each I and the value of each I. That's what this told me. Okay, I'm going to do another one that is a little more complicated. I'm a little worried of going over today. So here's my slightly more complicated one. So I got the same thing. I got 3 resistors, but now I got 2 batteries. And I say, okay, what's the current through each resistor? So I'm going to start this the same way. I'm first going to define all of my currents. And I like to make life easy that say normally current 1 is through resistor 1, current 2 is through resistor 2, current 3 is through resistor 3. So I'm going to define them like that. Now for direction, I got to just pick directions. And what I can say is, okay, I'm going to say it's going to push the correct way through resistor 1. And for some reason, I decided both the ones on the right are down. Why I picked that decision? Once again, it's arbitrary. Actually, I know why I picked this decision, is I stole this diagram from the textbook, so I just picked this direction to match the textbook. But it doesn't matter which direction you pick. And I said, okay, current 1 is coming in, and current 2 is going around like this. Current 3 is going around like that. So, junction rule. Junction rule, I'm going to look at my junction. I1 and I2 go into this junction. I3 comes out. Nice and simple. Loop rule. I got to pick my loops. So I'm going to pick a loop to use. And I picked this one, the big one. So, okay, that's my first loop. Now, when I go around that loop, I start by going up on I2, R2. And as I go up I2, R2, I'm going in the same direction as I2. So it's going to be negative. Then I go over this battery. When I go, and here I'll keep it with I'll do it like this. So I'm starting with going up this way. I'm in the direction of the current as I pass this going up, so it's negative. The battery, I'm going from positive to negative. I'm going the wrong way on this battery. So this is also negative. Keep going. And then I pass over all three. But all three, I'm going with the current. So this is negative I3 all three. And there's my equation. I started for my second loop to do this one. And I'll go through and try to do the same thing. So I'll go up, nothing happens. Then I pass over my first battery. I pass over the battery going negative to positive, so I add it. I pass through over all one with the current, so I subtract it. I pass through this one with the current, so I subtract it. And there's my three equations. There's a third loop I could have done. I could have just done the top half. It would have worked too. Now that I have my three equations, I can solve. So I'm going to look at this guy and say, okay, this bottom equation, I'm going to add I1 all1 to both sides. This is what I'm doing it the way I said I normally do, is that all threes and or I3s in both. So I'm going to not solve for that. I can then take the bottom equation, divide both sides by all1. Meanwhile, my other equation, I'm going to take this and say, okay, I can add I2 all2 to both sides. And let's divide both sides by all2. So now I have an equation for I1 with respect to I3, an equation for I2 in respect to I3. And this is going what I said before, as I started to say. If I want to solve the two, if whatever's in both of them, I3 is in, whatever in both loop rules, I3 is in both loop rules, solve for the other guy would normally make your life easier. Because I'll take this I1 and I2 and shove it into my junction rule and say I1 plus I2 equals I3. So making some space. I'll say, okay, you know what? I'm going to have to multiply by a common denominator. I'm going to multiply both sides by all1, all2. Because if I multiply both sides by all1, all2, I can get rid of these fractions. When I do that, my first term in the parentheses, the all1s cancel. The second term in the parentheses, my all2s cancel. And I get this mess. I can then factor through both sets of parentheses, where this is just literally me factoring in the all2 and factoring in the all1. I'm then going to take everything with an I in it, and I'm going to add it to both sides. I'll then factor out my I3 and divide. The math is ugly. I'm sorry. Deal. And I'll plug in my values. Do some math, get an answer. And there we go. I3 is -1 amp. Now, I know I got a negative value. That's okay. Keep working with that negative value. Wait to the end to deal with what that negative means. For now, just ignore it and keep going. See, earlier, I gave these two equations for I1 and I2. And I'll plug in that -1 amp to both. Plug it into I1. Plug it into I2. And now I have all three currents. I1 is 2 amps, I2 is -3 amps, I3 is -1 amp. I say, okay, that's my currents, 2, 3, and 1 amp respectively. However, I got some negatives. What those negatives mean, all those negatives mean is my directions are wrong. And I say, okay, I2, direction was wrong. I3, direction was wrong. Told you, it's an arbitrary guess. So I say, okay, it's like that really. And there you go. My current in I1 is 2 amps, and it's going, well, it's going up there and down through O2. My current through I1 is to the right through the resistor. My current of I3 is to the right through resistor 3 and upward the part I marked. I know the magnitude and the direction of each current. That's Kirchoff's rules. They suck. It's probably going to be the third problem on your first exam. Have fun. Okay.
All right, looking forward to it.
Yep. Bunch on the homework too. I hate them. This was like my least favorite thing in physics too, just because the math is ugly. I try to make the numbers work out nice, but they don't always. Okay. I'm going to leave that aside for a second. And this should have been earlier, and I got to fix my notes for this. This is what I was talking about the EMF on a battery. In these problems, I was just saying these batteries supply 14 volts and 10 volts respectively. Really though, batteries are more complicated than that. Batteries don't just supply a voltage. They do all sorts of weird things. They supply the voltage, but it's more complicated. What it is a battery will have some voltage it adds, but we often refer to the voltage supplied by a battery as the EMF, or electromotive force, because this is the force that gets the electrons moving, electromotive force. It's not really a force, voltage isn't a force, we know that, but that's just how it's viewed. Electromotive force, or EMF, which uses that symbol E, it's a voltage. The reason it doesn't get a special symbol, there's a few reasons, but basically it's always there. A battery is waiting to push that out. And if you go through like Ohm's law, if we have no current, we must have no voltage, right? Logically, V equals IL. But the electromotive force, it's always there. That it's a current waiting to drive. And so it gets its own symbol just so we don't have to deal with how it messes up Ohm's law. That whole V equals IL bit. I very seldom bother with the EMF. I normally just say a battery has a voltage V. But just to be clear, E is EMF, it's the voltage of a battery, it's measured in volts. V is the voltage. Any equation we've ever done with V, you can use EMF instead. As I said, it's weird that they all kept apart. Also, really, a battery applies a voltage, but a battery also has resistance. The EMF is the ideal resistance supplied by a battery. That if a battery was perfect, how much it added. For any battery, we can have an internal resistance, normally represented with a lowercase o. And we can say really the voltage coming through a battery is whatever the EMF is minus the internal resistance. For this reason, batteries are sometimes drawn as a power supply and a resistor right next to it, as I show in this bottom right. That's just to say, let's say we have an ideal battery attached to this resistor, instead of, let's say we have one real battery. It's just an easy way to deal with it. That a real battery is just a battery and a resistor shoved together. That means really if you have a simple circuit like this battery to resistor that I have here, I really should view this as having two resistors, the resistor attached and the internal resistance of the battery. If I go through my Kirchoff loop, I can say 0 equals the EMF minus IL minus IL, which rearranging means you can find the current due to a battery. This is a weird minor thing, as I said, that I just want to point out. For the most part, we're going to work with ideal batteries. I'm not going to worry about the internal resistance of a battery. I'm going to give you something like this circuit here, and I'm not going to say this battery has this resistance. But that's the general idea. All right, let's do a problem on that. Let's say we got a 24 ohm resistor connected against a 12-volt battery, and a current of 482 milliamps flows. What's the internal resistance of the battery? Use the equation we just said. I'll write down the numbers I just said. If I subtract I capital O from both sides, I can then divide both sides by current, plug in, and find the internal resistance. So it's actually measurable because of this. That if you just take a battery and hook it up to a known resistor of a set value, if you add an ammeter, you can always find the internal resistance of any battery. If you're doing something precise, it might be important to know what it is. Okay. Now, one of the things I said I was going to do today is I said I was going to talk about how to work out the current or voltage if we have not just resistors, but if we have capacitors also. And I don't go too explicitly with what I'm about to do in the notes, but I'm going to do it here instead. I have to put this in the notes later on. Let's say I have this setup. Battery, and just pretend it's ideal, resistor, capacitor. If I try to do the Kirchoff loop, I can say, okay, the battery adds a voltage V. The resistor drops a voltage of IO. But the capacitor, if I talk about the voltage drop of a capacitor, the only equation for voltage on a capacitor we have is Q equals CV. Therefore, the voltage drop is Q over C. But now this gets really weird because if I want to solve this for current, or if I want to solve it for charge, either way, I kind of have this I and Q term. I have an I, I have a Q. I have to do something with one of them. And they're actually related. See, you might remember we said that current is change in Q over change in time. Really, that was a shorthand. It's actually a derivative, but this is algebra-based physics, so I'm not doing derivatives at the moment. But if I shove this I into here, I can get, and if I do it with the calc version, so I'm going to hint at the calc version despite it being calc-based physics, V minus dq dt all minus Q over C equals 0. I can get this weird thing where I have an integral, or sorry, a derivative and this other piece. And what you can find is using this Kirchoff loop and a bit of calculus, you could try to solve for the current through a Kirchoff loop. And what you get, yes.
On the last page you were just on, that's not like a partial differential equation. That's just a derivative, right? Because it's just how your d's are looking to me.
Oh yeah. This is just a derivative. It's not partial.
Okay.
I do so many partial derivatives that I often just do a slightly more cursive d by mistake.
Okay. I was just curious when you were saying derivative and it just looked like a partial differential. So
Nope. It's
right.
not partial.
Okay.
For those of you who don't know calc, ignore that. So what's going to happen is that when I go and do this math, which as I said, I'm skipping because that's calculus, just trust me, the math works. You get that Q is a function of time. And here's the thing. If you hook a battery up to a capacitor with no resistance, it's going to try to put all of the charge on it. It's going to instantly go from Q equals 0 to Q equals CV. However, that's really bad for the circuit. Instantly dumping all the charge in can destroy the capacitor or the battery or both. When you add the resistor, that setup makes the current happen as a function of time. And as you add the resistor, what's going to happen is instead the charge will slowly build up. And instead of just being no charge, all the charge, it'll be no charge, some charge, going up, going up, going up, full. And if you actually do the calcul, you can find the charge as a function of time. Now, this is called an RC circuit because it has a resistor and a capacitor, RC. And what you'll find is that if you have an uncharged capacitor, the charge as a function of time goes as this equation. Q equals Q naught, parentheses 1 minus E negative T over RC. In this equation, Q naught, is the max charge, where the max charge will be the capacitance times the EMF of the battery. RC will sometimes use the symbol tau. So it's called the time constant because it relates how fast it goes. So you sometimes see a tau there, you sometimes see an RC there. And what it says is initially when time equals 0, there's going to be no charge. And as time goes up, the charge will get more and more and more until it hits a max. After it hits that max, there will be no current because all the charge will be there. Now, one thing I want to stress here is I said what Q naught is. I said what R and C is. That E there is Euler's constant. It's a constant, 2.71828. On a calculator, you see a lot of things just with an E to the power of. It's the inverse of natural log. So anytime you see a natural log, that's how you undo it. But that'll be the charge as a function of time. Likewise, we could say as the charge goes up in a capacitor, the current through the resistor is actually going to drop. And the current through the resistor as a function of time will be given as this equation. And I can show this. Well, so this is as you charge it up. I'll come back to, I'll show it in a second. What this does is it puts a lot of charge on the capacitor, slowly, following these equations. And once all the charge is on the capacitor, if you go and just remove the battery, the capacitor basically turns into a battery. Because think about a capacitor, right? When you charge a capacitor, it gets positive charge on one side, negative charge on the other. And look at my picture of a battery. It's positive charge on one side, negative charge on the other. Once the capacitor is fully charged, it stops the circuit from happening because it basically balances the battery. The battery is trying to push current one way, and the capacitor is trying to push current the other way, and they cancel each other out. However, if you remove the battery, the capacitor would discharge. And the charge as a function of time will go as follows, working like a battery. We can also say the current as a function of time. So here it is all at once. Charging a capacitor, this is how the charge goes as a function of time, the current goes as a function of time. Discharging a capacitor, there's the current and charge as a function of time. And what we're going to do is we're going to open up a video and we're going to play one. So here we go. I got a capacitor, that's this big blue thing. The resistor is going to be a light bulb because that's what a light bulb, an old school light bulb is. It's a resistor. And I'm going to start it charging. You can't really see charging. You just got to trust me it's happening. But I'm then going to go, and once it's charged, I'm going to discharge through the light bulb. And what you'll see is as it discharges, it goes down. It goes down because the capacitor is basically running out of charge, and it's slowly dying out. The current is going down as a function of time. And let's do a problem. How long does it take the charge on the capacitor to drop to 1/4 its original value in multiples of tau? Tau is the time constant. And it didn't actually say this, I probably should have, but you see there's no battery here. So we're gonna assume we're discharging. It's dropping to 1/4, we have to assume it's discharging. If it was charging up, it wouldn't be dropping, right? So I say so this is discharging, how long does it take the capacitor to drop to 1/4 its original value? Well, this is discharging, we're talking about charge. So I use this equation. 1/4 the original value is when Q over Q naught is 1/4. But Q over Q naught is E negative T over RC. What I'm going to do if I want to solve for this is I have to take the natural log of both sides. The natural log of E to the negative T over RC is negative T over RC. Now I said in multiples of tau, tau is RC. I'll then multiply both sides by negative tau. And I can try to solve. Now, I kind of skipped something here, but I need the natural log of 1/4. The natural log of 1/4 is negative 1.39. I didn't show that, but it's just the natural log of 1/4 is negative 1.39. So that means T is 1.39 tau. The next bit is, given a voltage, resistance, capacitance, find the initial charge of the capacitor and the time it takes to discharge to 1/4. Well, the initial charge is just the max charge. So it's C times the EMF for the battery. Now I wrote V equals 12, but voltage is the same as an EMF. And the time, I said the time was 1.39 tau. So it's 1.39 RC. So I can plug in and get a value. Questions?
Not yet.
Well, if not yet, then there's none, because that's the end. That's this chapter. Homework is due tonight, as in the 16th, for those of you watching the video later, although not, judging by my views on YouTube, no one's watching the videos on YouTube, so that's cool. Being said, everyone's just going to fail the class because so few people actually come to it and no one watches the videos. Yeah, I'll put example problems up today at 3:50, which is in 2 minutes. And Friday, we're going to solve examples. But other than that, there you go. Sorry for the weird mess up in autos with EMF in the notes. I will be fixing that because I suck. This is what happens when I'm doing a new class. There's mistakes in the notes. Other than that, have a good day. I'll see you later.
Yeah.